Okay, good morning everyone. Today, this lecture is going to be our last lecture this semester, and my plan is to finish shadows in OpenGL. We are going to see two algorithms, shadow volumes and shadow mapping, and I will also show an implementation of shadow mapping algorithm. I will show you an example. Let me just show you how it will look like, and I will show you the code. And also, we may run a little bit late today in order to finish all the topics. I may require some extra 10 or 15 minutes, so feel free to leave the Zoom meeting if you have other classes right after this one, or if you have other meetings, okay? So you may watch later the recorded one. I plan to finish all of the slides today. So this is an implementation of the shadow mapping algorithm in action. As you can see on the screen, there are dynamic shadows here. I wanted to show this dynamicity as an animation of jumping spheres. Okay, so this is something I implemented a couple of years ago, maybe 5-6 years ago. And we can also change the light position with some keyboard. I think the keyboard C. And when I press C, I change the lights position, which changes all the lighting in the scene, also the shadows directions. As you can see, shadows change direction also dynamically very quickly. And I also left this part here, this corner of the table, as you can see, and also the other corner is like in shadow, to show you the artifact of when certain objects are outside the viewing volume of the lights viewing volume, the lights perspective frustum, they also are considered as in shadow. So that's an artifact that you need to make sure that the entire scene is inside the viewing areas to have the shadows. Okay, so you can also there are also keyboard mappings to go to on top of spheres. Also objects cast shadows on themselves as well. So let's see, maybe this is not a good one. Yeah, maybe the original view. Yeah, as you can see, objects cast shadow on themselves on the table. So this is this implementation was already there in example code on my website, but I took it took like 20-30 minutes to convert the old GLUT version and Glee. It was using Glee library for the extension, OpenGL library, and it was using GLUT for window management. It just took 20 or 30 minutes just before class today to convert everything to GLFW and Glue. So I will share this GLFW and Glue version with you on OttiClass, so you can take a look at how it is implemented. All right, so here it uses two different shaders. Simple shader. These simple shaders are the simplest you can get, which only changes position, and these simple shaders are used to render the scene from the lights perspective, because with these simple shaders we don't actually need the rendered scene. All we need is the depth buffer in the shadow mapping algorithm. So these simple shaders do not spend any computational resources, just do the very basic stuff of programmable shader. The actual shadow mapping algorithm in the programmable shaders is implemented in this vertex shader and in this fragment shader that we see here. They're also not very long, as you can see, 50 lines of code for the fragment shader and only like 20 lines of code for the vertex shader. And the code itself, which makes use of frame buffer objects to render the scene from a light's perspective and get the depth image as a texture is here. So this code is a little bit long. It has all the sphere drawing, saving of the lights, the model view projection matrix from the lights perspective. Also, it uses not the modern OpenGL version, it uses the old OpenGL version in which you use for example, GL translate, GL rotate. Let me just show you where they are, where we do the drawing. Yeah, here. GL matrix mode, projection, load identity. In an orthographic view, we get the light MVP matrix and orthographic view. And as you can see, the tabletop is also the tabletop is drawn since it's done at the shadow is done at the fragment level. We don't need to subdivide the table into smaller triangles. We can actually draw here we have two large triangles, these big and GL triangles draw, there are 6 vertices here. It draws 2 large triangles, which is that tabletop we see. And it draws each sphere again by making use of the GL utility function GLU sphere to draw spheres as a quadric. And I think this is like maybe the subdivisions. It uses it divides the quadric into 40 units in the x-axis and in the y-axis. So this is how detailed you want your sphere. It's actually made up of polygons. It just shows how many polygons you need. I think each sphere is like made up of 1600, I mean 40 by 40, 1600, or if you multiply it by, well, if it's made up of quads, maybe there are 1600 quads here, but it's basically using a utility function to draw the spheres, because in OpenGL there is no draw sphere. There's no sphere primitive in OpenGL, so we need these additional utility libraries to draw the spheres. And yeah, I'm going to talk about the algorithms. The shadow mapping algorithm is going to, we are going to talk about it second. The first algorithm we are going to talk about is called shadow volumes algorithm, which is a completely different algorithm to have shadows in OpenGL, and there are no built-in OpenGL shadow functionality. So therefore, we have to take care of the shadows ourselves by writing this code manually. But in ray tracing, it was not so difficult to add shadows by producing these shadow rays and checking whether we already have the intersection of rays with objects. We have that function. So, oh, by the way, am I recording? Yeah, I'm recording. Basically, we just check the same, we use the same intersection function with the objects to see whether there's an intersection with an object between the light source and the point that we're interested in. So here there is no function in OpenGL like GL make shadow. There are several shadow algorithms, and they may not be so easily implemented, but they can be implemented using features of OpenGL. So this is actually an advanced version, OpenGL programming that we have to do to have this shadow mapping implemented, or shadow volumes implemented, because all these buffers, stencil buffer, the frame buffer objects, they're not just simple OpenGL primitive drawing. So actually, maybe we can drop this easily out here. They can be implemented. I don't know how it was not so easy for me to implement the shadow mapping algorithm. So we are going to see 2 algorithms in this course, the shadow volumes and shadow mapping, and these 2 algorithms will be the last things that we cover in this course. Okay, as I said, let me repeat, we are not going to talk about curves and surfaces. Both algorithms, both of them have advantages and disadvantages, and there are many variants of even shadow volumes and shadow mapping algorithms. For example, you can have soft shadows, hard shadows. You can take into account transparent objects, different things, and it's still an active research area to efficiently get these shadows. In 2011, for example, although these algorithms are really old, it makes you wonder how in 1978 they had an implementation of shadow mapping without the programmable shaders. Okay, so it's really, the algorithms are really old, but with the help of programmable shaders, we can parallelize these algorithms and have real-time dynamic shadows in OpenGL. So we are going to study the basic versions of this algorithm. So let's go ahead and start with the first algorithm, shadow volumes. So this shows a picture here where we have the light source and we have a simple object like a triangle. This triangle actually casts a shadow for any object that is behind it, right? If we have any object in the volume behind this triangle, If it's inside the volume, which we call the shadow volume, which extends to infinity actually, but we can actually cut this out with some quad or with some polygon at the end of our scene. If there are no objects beyond that point, there is no need to consider this shadow volume all the way to infinity. But just think about, look at this volume behind this triangle. If we only have this light source in the scene, any object within this volume will be in shadow. So our goal will be to find such objects within the shadow volume as fast as possible. Another thing is, first of all, we need to create this shadow volume. So the shadow volume algorithm works in stages. The first stage composed of basically creating these shadow volumes for every object. So if you have objects as shadow casters, for every shadow caster object, you need to create the shadow volume corresponding to that object. And you may have multiple shadow volumes in your scene. So we need to create these as real geometrical objects. Although they are like abstract entities here, this shadow volume is something that is abstract, right? I mean, it's just because of the positioning of this light and this triangle. If you're inside this volume, a geometric object will be in shadow. But the first stage of the shadow volume algorithm is to create this shadow volume as a concrete, physical, geometric object. We are not going to render it, but we are going to create the shadow volume. And after that, by using the front and back faces of the shadow volume, we are going to render those front and back faces in different stages, and also render all of the objects in the scene during the process, to figure out quickly whether an object is within the shadow, inside the shadow volume or not. Okay, so that's basically shadow volumes algorithm in summary. And how we are doing this, how we are determining whether an object is inside, outside, we are going to be using, shadow volume algorithm is going to use both the depth buffer and the stencil buffer. A stencil buffer is going to be used as a counter. We are going to, at one pass, we are going to increment the stencil values in the stencil buffer by 1, and at another pass, we are going to reduce them by 1 again. For things that are 0, they are going to be outside the shadow volume. Objects that remain 1 are going to be inside the shadow volume. So stencil buffer is going to be used as a filter then to render the objects with the additional lighting, diffuse and specular. So and ones that are that they have their stencil values to certain value, they are going to remain in shadow, and only the ambient color of them will be used in the rendering process. So let's go ahead and start quickly at about each step, and I'm going to show you some code and how each step is implemented. All right, so for a teapot, again, this is our Utah teapot. Modeled as a piecewise linear with piecewise linear combination of these quads. And if we have a light source here, there will be a shadow volume behind it. So a contour edge here, the first step of creating the shadow volume is find the contour edges of the object that so the light sees the object. Certain polygons are going to be completely in the inside the frontal view of that object, and there will be certain polygons in the boundary of what the light sees. So these boundary edges, we call them contour edges or silhouette edges. Okay, as seen, they are for an object as seen from the light source. And here a contour edge is defined in such a way that, so we are only talking about objects that are in closed form like this, in which they are like two-dimensional manifolds with polygons in which each edge is adjacent to two polygons like this. Okay, each edge, I mean, in a normal closed form object like this, an edge should be adjacent, not adjacent, incident. An edge should be incident on two polygons, Okay, so this incidence, for example, you see this, let me try annotate here. You see this edge here. It is incident on this polygon number 1 and polygon number 2. If the light source sees this polygon, but it does not see this polygon, okay, and how do we figure out it sees this polygon and does not see this polygon? Same as backface culling. We are going to use the normals of these polygons, okay, and do a dot product of these normal with the light source direction. This polygon is facing the light, but this polygon is facing the back face of this polygon is facing the light. So therefore, if there's an edge in which the two incident polygons, one of them faces the light, the other does not face the light, this edge will be identified as a contour edge. So we are going to keep a set of contour edges, and by using them, we are going to have the front view of our shadow volume, and these edges are going to be extruded from the light source. We are going to draw rays to the vertices of these edges, and this is called extrusion. We are going to just extrude the edges all the way to infinity or to some faraway volume to have these to create this shadow volume geometry. So here is how it's done. So yeah, this is also trying to show the same thing I already in the previous slide. One adjacent polygon facing the light. So the two polygons are adjacent to each other, and this edge has two incident polygons, is incident on two polygons. One of them is facing the light, the other is not facing the light. So therefore, just like backface culling, we use dot product to decide whether a face is toward or away from the light source. And here's a pseudocode from John Siombicas, which implements this contour finding, finding contour edges pseudocode. We have the light position in which we multiply. We first get our light into the world coordinate system, and for every polygon, okay, every polygon is going to have a number of edges. For every edge of a polygon, as you can see, we first find the light direction. It's like the view vector. So it uses the average polygon position. I think it could use any vertex of the polygon as well, just like we did in backface culling. So it forms this vector. This becomes the light vector, and it uses the dot product of this light vector with the polygon normal. If it's greater than 0, it means that this is a back-facing polygon. And for every edge of the polygon, if the edge is already in the contour edge list, okay, it means both of the faces are facing away from the polygon. If both of them are facing away, then it cannot be a contour edge. So it's remove the existing edge from the contour list if it's already in the contour edge list. If it's not in the contour edge list, we add it to the contour list. So since every edge is incident on two polygons, every polygon is adding all of its edges, but if there is a back-facing one, it's going to remove it. If there's an already existing edge there, the back-facing, one of them is going to add, the other is remove. If both of them are back-facing, both of them are going to. So one of them is going to add, the other is going to remove. So the edge is not going to be on the contour list. So for front-facing objects, so this is for this. Else is for this one. So if it's a front-facing polygon, we add it to the contour list. Okay. So if they are, let's see, if they are, if it's a back-facing polygon. Let's see. Sorry. This else does not belong to this. If this else belong to this one. So we are only adding the contours for back-facing polygons. Okay. If we find a back-facing polygon, but if the other is only, it will remain in the contour list only if the other incident polygon does not remove it from the list. Okay, so if it removes it, this is going to be the case where both polygons are back-facing polygons. For front-facing polygons, we don't add any contour edges for front-facing polygons. Okay, but the fact that the edges in the contour edge list means that one of it's front-facing, one of it's back-facing. It has to have a back-facing polygon that adds this edge to the contour list. So after we have the contour edges, we have a list of edges. They have vertices, two beginning and end vertices. By forming rays to each of these vertices, we extrude them to infinity to form this volume. So here, this extrude magnitude, a big number here to have, we make sure that this big number ensures the entire scene is inside the shadow volume. So for every edge, we create a quad by extruding, by using the two edges of that contour edge, and by extruding those edges, we create a quad. Just let me try to draw it here on GIMP. So imagine this is a contour edge. This is where the light source is. So I'm just focusing on one edge. So this one becomes one vertex. This one becomes another vertex. By using in this direction, we extrude this and create two other vertices here, okay, in a faraway direction. And this becomes a quad that we add to our shadow volume. So this is what this is saying. These are the four vertices of the shadow quad. And after that, this becomes, we also cap it. We can have a polygon at the back end, or we can, and we also have this polygon in the front of this. So this becomes our shadow volume, and this one visualizes some of the shadow. And for complicated objects with lots of holes in them or complicated shapes, the shadow volume may be quite complex. Okay, for a complex object, the shadow, and this actually causes some artifacts. Shadow volume may not be a very good algorithm if you have complex objects like this. And sometimes you use a simpler version of the same object as a shadow caster. You don't need to have the entire, because if your only goal is to create the shadow volume, you can use a simpler, low resolution model of your object to have these shadows. Your shadow, if you're not interested in details in your shadows, you can have a more crude version of the same object. Now, and then we come to, after we create the shadow volumes, the next thing is, how can we distinguish between parts of an object that are inside the shadow volume and that are outside the shadow volume? So this is done by trying to not making a query for every object, but we proceed in the image space by the fragment level. So at the fragment level, we have to distinguish between the fragments. For example, this may be a quad, this may be the same primitive. Part of the primitive is in shadow, part of the primitive is outside the shadow. So our algorithm proceeds in the frame buffer space to distinguish between the parts in shadow and parts not in shadow. So the difference, as you can see here, is that this point is inside the shadow volume, while this point is outside the shadow volume. So what we do is this. We first render the entire scene by just using ambient color, okay, ambient only, because the objects that are in shadow will have their ambient color, right? So we render the entire scene only using ambient color, and we enable writing to depth buffer. So the depth buffer, so when I say we render the entire scene, we do not render the shadow volumes, okay? The actual scene objects are rendered. So we render this red sphere, we render this blue rectangular object, only these two, but we render them only in ambient color. No diffuse or diffuse and specular is not used at this point. And we also, when we are rendering the scene, we have a depth buffer that we maintain, which shows for this pixel, for example, what is the current depth value. Okay, so the depth of this position, the depth of this position, also wherever they fall on the frame buffer, in the depth buffer, those depths are maintained computed and maintained here in the depth buffer. Now, here is the thing. Before we render diffuse and specular, we need to make sure, diffuse and specular are going to be added only to this one and not this one. Okay, we don't want because this point is in shadow, this point is not in shadow. We need to have diffuse and specular for this one, but not for this one. Okay, so it's done like this. We use, at this point, we use both the stencil buffer and the previously computed depth buffer. So we have the depth buffer here. And we will have slides that show an example on this, but I just want to describe the algorithm on this figure overall. So now here is the part where we actually render our shadow volume objects and use the stencil buffer to do some counting. So what we do is we first render the front face of the shadow volume object. And when we render the front face, what we do is we use the increment function of the stencil. So stencil buffer could be used as a counter. There are functions that says increment the stencil buffer value by 1 if, for example, the current fragment passes the depth test. So what it means is that when we are rendering the front faces, if there are any objects that are behind this front face, for example, if there's another triangular object that is here, this is actually when we're rendering the front face of this one, when the camera is here, let me actually show this triangle somewhere here. If I have a triangle here, for example, if you look at this front face here, it doesn't pass the depth test. So therefore, for this fragment, since we are not going to be incrementing the stencil buffer. So what I'm saying is that while we're rendering the front faces only, this is a front face of from the camera perspective, it's the front face of the shadow volume, and we can make things like that. We can say GL render only the front faces of objects at that point, and while doing the rendering, do not put anything on the color buffer. Just during this rendering pass, just update the stencil buffer for those pixels who pass the depth test. So if this front face passes the depth test for this fragment, it means that this actual objects, this fragment is behind the front face. Actually, this one is also behind the front face. As you can see, this one depth value was this. So for an image, that pixel that is here, when we are rendering the front face, both of the values for the corresponding fragments, let's call it fragment 1 and fragment 2, both of those stencil values are going to be incremented by 1, and they will become 1 because the front face passes the depth test. Okay, now in the second pass, we this time render the back face of the shadow volume. And while we are rendering the back faces, this time we decrease the stencil buffer value for any fragment that passes the depth test, which means that for this fragment, which was far away, as you can see, when we're rendering the back face is also in front of this fragment, previously rendered fragment in the depth buffer. So this fragment passes the depth test. So it becomes fragment 1. So if this is fragment 1, fragment 2, this one is now decremented and it becomes 0. But what about this one? When we're rendering the back face of this shadow volume, there was an object fragment here which was in front of this back face, so this one fails the depth test, so it remains as +1 in the second pass. You see what we just did? We were able to distinguish objects that are outside the viewing volume. Their stencil values are now 0. If any stencil value is 0, it means that that fragment is actually outside the shadow volume. So any fragment that is inside the shadow volume is going to stay 1. And all we need to do is use the stencil buffer and use the values of 1 as filter to avoid computing diffuse and specular components for those pixels with stencil value 1. So that's the shadow volume algorithm in summary. Okay, so any questions up to this point? I hope it's clear. I'm going to proceed to the next slide, which actually shows an example of, it repeats everything that I just described. So now we want to find out whether we are not doing like ray tracing here. We cannot use rays. Okay, we have to work in fragment space. So we're, as I said, this is where we use depth and stencil buffers. Stencil buffer acts like a counter for every fragment, for every pixel, and we can clear the stencil buffer all to 0 initially, and we can initialize it by clearing everything to 0. And there are operations like increment and decrement operations based on the result of the depth test. We can say GL stencil operation, what happens when the depth test fails, what happens when the depth test passes, and it's basically a counter that we use for every fragment. So it's like you have, if you have a 1000 by 1000 image, it's like you have 1 million counter variables as your stencil buffer. So this one is a nice example that shows the color buffer, depth buffer, and the stencil buffer together. So this is where we draw a rectangle in which part of it is in shadow. So let's see, we draw the rectangle in ambient color. We get this 100, 100, 100 in this ambient color, and this is the rectangle is directly parallel to the XY plane. So it's all 0, 5, 0, 5, 0, 5 depth. Okay, so the depth buffer is updated. Then after this point, in the second and third stages where we are going to render the front and back faces of the shadow volume, at this point we disable writing to the depth buffer after the rectangle is drawn, because we don't want the depth buffer to be updated with the values of the front face of the shadow volume. We want the depth buffer to contain the depth of actual objects in the scene. All right, so after the first pass with the ambient light is complete, we disable, after that point, we disable writing to the depth buffer. And then we draw the front faces of the shadow volume. For example, if part of this rectangle was inside, part of was outside, but the part that is outside is on the other side of the shadow volume. So when we draw the front faces, all of the front faces are going to be in front of our rectangle. So therefore, all of the pixels pass the depth test, in which we incremented to 1. And in the second pass, the part that is in shadow, the lower part here that I highlight, the lower part that I highlight is in shadow. So it's in shadow means that it is in front of the back face of the, if it's inside the shadow volume, it has to be in front of the back face of shadow volume. So when we are rendering the back face of the shadow volume, those back faces cannot pass the depth test. So we are unable to increment the stencil value for parts that are inside the shadow volume. But for parts that are outside the shadow volume, they will be behind the back faces, so they're decremented back to 0. Now, we use the stencil buffer as a filter such that pixels whose stencil value is 0 will be rendered with the diffuse and specular component. So what we do is we render them here. Also, we enable writing to the depth buffer and clear it. We enable the point light source. We can also do additive blending. So the contribution of passing pixels will be added to previous ambient values. So that, for example, if we compute 50 as additional, the previous ambient, which was 100 there, is going to be blended with this diffuse and specular. So here is an example of, I mean, you can blend or just directly use diffuse and specular with no ambient, which will make your scene a little bit darker maybe. But that's basically the shadow volume algorithm, which makes use of stencil buffer to figure out which objects are inside, which objects are outside the shadow volume. As you can see, it's a very complicated algorithm. Here, the depth buffer change. In the second time we are writing, do we really need the depth buffer at that point? I'm not sure. Here we in the last pass, enable writing to the depth buffer. It changed because these parts are no longer, since the stencil buffer values were 1 here. So these fragments are not updated. These frame buffer parts are not, actually they stay 0. I mean, if we didn't have ambient, actually we're not drawing anything here in these pixels. That's why they stayed at 1.0. The parts that we were able to draw, the triangle, rectangle parts, actually this should be also 0.5. There's a 0.5 incorrect here, so it has to be 0.5. So the parts that we were able to draw the rectangle, we get back to the previous depth values. But this part remains 111 because those stencil values were 111 here, and we use it as a mask, not to draw to those parts. So we didn't draw with diffuse and specular. So the previous color buffer values of 111 stayed as 100, 100, 100 stayed like that. So it's like the parts that were in shadow are not drawn at all in this last pass. So that's why their values remain like this. But will it cause a problem for rendering for example, if there's an object that is, no, I don't think it will cause a problem, because these values are already belonging to, in the first pass, we already did correctly render the scene in which the front objects will appear at the front. So, and since this part is really masked out, it's in shadow and it's masked out, nobody else is going to be able to modify these parts. That's why it's like this. All right, so that was the shadow volumes algorithm, as you can see, which is very complex. It requires lots of passes, computation of the shadow volume geometry. It requires lots of processing of scene geometry to create a shadow volume. Needs to be updated if lights or objects move. I mean, just imagine if you move your light, the entire geometry of the shadow volume changes. So you need to reconstruct your shadow volumes for every object. It can be time-consuming for complex geometry, so we use maybe simpler versions of them for shadow volume generation. And there's multiple rendering paths. We first have an ambient pass for each light. Each light has a different shadow volume. We have the front face, back face pass, and the final diffuse specular pass for that light source. And we do it for every light source, so it's really time-consuming. But the good thing is that all these different passes, when you have the GPU, they are highly parallelized in that fragment level. If you have 1000 cores, it means that you're doing it in 1000 parallel processors simultaneously. And if only the camera moves, you don't need to update the shadow volume. Shadow volume is only going to change if the light source changes or the objects change position with respect to the light source. And here are there are shadow leaks that may happen if your shadow volume is not created correctly. Leaking artifacts. Look at this, the shadow looks very bad. And yeah, one way to speed up is to use low resolution versions of the models for casting shadows. And there are different possible extension, different questions you may need to answer if you're really going to implement this as well. I'm not going to answer these, but just know, as some thinking points, what will happen, for example, when the camera is inside the shadow volume. When you render the front faces are behind you, so what happens? Yeah, so you have to think about these special cases like this. But yeah, multiple light sources, multiple shadow casters, transparent shadow casters. So all these are, some of them are answered in these links. But yeah, these are detailed parts that we're not going to cover. Now, yeah, we come to our last algorithm. We have like 10 minutes left until the end of the class, but I think I will be able to finish it 15 minutes or so. I'm not going to use more than 5 minutes of your time probably, because I already explained shadow mapping earlier on Tuesday. So you know how the shadow mapping algorithm works, and it's much simpler than the shadow volume algorithm in terms of implementation. We don't need to have these additional geometry at all. It only uses the depth buffer and nothing else. And for additional data, it uses the model view projection matrix from the light's perspective. All we need is this. From the light's perspective, we need the model view projection matrix, and we need the depth buffer of the scene, which is rendered from the light's perspective. So this was in a 1978 paper, casting curved shadows on curved surfaces. It's an image space technique similar to shadow volume. Shadow volume also has some object space task, right? The shadow generation of the shadow volume was done in the object space. So shadow volume algorithm in that sense is a like it uses both object space parts and image space parts where you use the stencil and the depth buffer. But this shadow mapping algorithm is entirely image space technique where we work only on the fragments. The advantage is that there is no knowledge or processing of scene geometry is required beforehand. We don't need to use a stencil buffer, and we need fewer rendering passes than shadow volumes. And disadvantage is that it still requires multiple passes. We have to have one pass for every light source. And there may be some aliasing artifacts that may occur, like you have seen here. This was an artifact, these corners of the table where the shadow, we render from the light's perspective with some volume, and therefore things outside this volume will be like in shadows. But as you can see, it's pretty fast. I mean, we can render in 30 frames per second, which is really smooth. And don't forget, we're using not the modern OpenGL in this implementation, just with GL triangles and everything. So the algorithm is like this. We first, part one, render the scene from the point of view of the light source, as if the light source was the camera. The thing is that if your camera is exactly at the point of the light source, there are no shadows. If what you're seeing is, it's also basically saying that if you have a camera with some very powerful light attached to your camera, there shouldn't be any shadows in the scene. Whatever you see should be highlighted and lighted nicely. So objects that are not visible from the point of the light, point of view of the light, they are in shadow with respect to that light source. Now, in the second pass, we need to determine now, because our camera is not in the same place as the light, in the second pass, we need to go back to our camera and ask this question for a fragment. We need to basically ask this question for a fragment. Was this fragment visible from the light's perspective? Okay, so this is basically what we're asking. Let me use a different one here. So imagine we have an object here, a rectangular box, and we have some light here. We have a camera here. We are looking. Now we have, for example, another object, a sphere here, in which the camera sees that sphere. Okay, so here is, we have an image in front of the camera. So this is our image with lots of pixels, and this sphere's point is in this coordinate on this image. Now what we ask for this fragment is, this fragment belongs to this projected sphere point. We ask whether light sees this point on the sphere. So how do we do that? It's very simple actually in terms of idea. Idea is really genius. It's basically when we render from the light's perspective, there's also an image in front of the light with all those pixels. Now, if this rectangle has a fragment which actually is in front of this sphere point, what will happen is that this rectangle's depth will be the one that is stored in the depth buffer here. And what is the depth of this rectangle point? We find the depth of that rectangle point after we multiply it with the model view projection matrix of this rectangle point. Let's call it RP, rectangle point. We get the depth of the sphere's point, let's call it the sphere point, SP. If we multiply with the same MVP from the light source, we can get the z value, the z component of this projected sphere point will be the depth of this sphere point from the light's perspective. And the one that will be written in the depth buffer will be the one that belongs to this one. Okay, there are two depths here, depth of sphere, depth of the rectangle point. And in our depth buffer, in some pixel, wherever pixel this, both of that, assuming that they both, I'm giving an example in which both of these points are projected onto the same pixel in the depth buffer from the light's perspective, the one that is written on the depth buffer will be dr, because that's smaller than ds, right? Now, all we need to do is, when we are rendering from the camera point of view, what happens is that the same sphere point will actually be completely in a different pixel. I mean, we cannot just go ahead and look at the depth buffer at this pixel. As you can see, it's a wrong pixel. The same sphere point, when we multiply it this time with a different MVP, this is MVP of the camera, the same point, okay, the same sphere point is this time when we are rendering from the camera perspective, it's rendered to a different pixel. It falls into a different pixel here, this fragment, because it's a completely different view, okay, completely different view angle. Now, we cannot directly just use the pixel coordinates of this and use that to query the depth buffer. What we need to do is, we need to get this SP, multiply it with this MVP to find its ij coordinates. We need to find the correct ij coordinates. So these ij coordinates in the depth buffer are the correct ones. We need to, and we can find those ij coordinates by just asking, where would this SP be projected from the light's perspective? It's not difficult to find that. It's not difficult to find that if we have the light's model view projection matrix. So we use the light's model view projection matrix, model view projection matrix, for two purposes. After we project SP with light's model view projection matrix, we use the XY coordinates of the projected point to find which pixel to look up in the depth buffer, and we use the Z coordinate of that to get the depth of SP to get basically this DS, okay? Now, all we need to do is this simple check. If ds is larger than the value that is stored at this ij pixel in the depth buffer, then that sphere point is in shadow. If it's equal to this value, since we're dealing with floating point values, we don't directly look at equality, but we just say if it's close enough to that within some epsilon, which means that that's actually the fragment that the light sees, so it's not in shadow. Okay, so the entire algorithm is simple. So here, so this is the light source view. As you can see, from the light's perspective, there shouldn't be any shadows. And this is the original camera view. We usually use orthographic projection for directional lights because the light rays are parallel to each other. For spotlights or point lights, we may use perspective projection when we are rendering from the light source. And then the only thing that we need from the light's perspective is the depth buffer, and we use off-screen rendering. We have stored this depth buffer onto a texture map as a frame buffer object. And here's a display of that depth buffer from the light's point of view. When we are rendering it from the camera's point of view, for every pixel, we compare the depth value of that pixel with respect to the light source to the stored value in the depth texture that was computed from the point of view of the light source. So if they are equal, it means that that's the fragment that the light sees, which means that we are not in shadow. If not, if R is greater than D, is it possible? So the third case, R is smaller than D, is not written here. Is it possible? No. I mean, unless ignoring floating point imprecision, it's not possible. I mean, the object cannot be closer. I mean, if it's closer, that should be the one the light sees. Okay, so if that's the object, I mean, that's only possible if in the first pass you actually did not render the object, and in the second pass you render a different object. I mean, if you render different scenes with different sets of objects, this may happen, the third case. But if you're just rendering the same scene twice, you either get this equality, which means that that's the point the light sees, which means you're not in shadow. If it's greater than D, it means that if there's some other object in front of your fragment from the light's perspective, so you have to be in shadow. Okay, so when I say when there is a problem, it's referring to this thing where we cannot directly query this ij coordinate. We have to in this depth pixel, the coordinate is not the coordinate is found correctly by using the light's point of view, because the light and camera have different orientations. So this one also is showing the same figure that I have drawn on GIMP from a different perspective. And after that, all we need to do is, if this impulse represents the roll coordinate of an object, and we compute its camera coordinates by multiplying with the camera, only the model view matrix. So this is the position. Also, we project it off at the camera. So this is this camera position, and its light view coordinates are multiplied by multiplying the vertices position from the with the model view projection matrix of the light. Okay, so then we use this outpost light. Its first two values are used to query our depth texture, and its third value, its depth, is used to compare those two depths. But what happens is that in this canonical viewing volume, all the coordinates are between -1 and 1. So, but in order to be able to use them as texture coordinates to query as if they are to get the pixel coordinates as if they are texture coordinates between 0 and 1, these -1, 1 should be converted to be rescaled to 0, 1. And that's where this bias matrix, in the source code, you're going to find the matrix that we multiplied the MVP with. This is what it's used for. Scale everything. So if you look at what this one is doing, it first adds 0.5 to that and scales them by half. Okay, so first, so we multiplied, this will bring it all, so if you just divide it by half, it will be between minus 0.5 and plus 0.5. If you add 0.5 to those values, it will become between 0 and 1. So this is what this bias matrix is. Convert everything between in the canonical view volume, which was between -1 and 1, bring it back to between values 0 and 1, so that we can use them as texture coordinates in our depth matrix. So this is what we use. We do a texture lookup by using the xy coordinates of our light position fragment, and then we use its z value. Okay, so this z value is the r correspond to that depth of s, ds, that I had in the figure, and this d correspond to depth of r that was stored in the depth buffer. So this is the one that is stored in the depth buffer. This is the depth of the fragment we have here. If so this one, if it's greater than that, if r is greater, it means that we are in shadow. So I mean, we don't do shadows like this, right? We don't just darken the color. We actually if you're using ambient, diffuse, and specular, so this is like a cheap trick to do the shadow. The actual shadow is not done like this. So what we do is if it's in shadow, we just render it with the ambient color, else we render it with ambient, diffuse, specular color. Okay, so in the else part, you have to compute diffuse and specular for this light source and add them to the final color you're finding. So the actual shadow is not done by just adding and multiplying with 0.5. I mean, if you look at the code that we have here, in the shadow shader frag, what we are doing is we're computing diffuse, ambient, and specular, all of them. And here, what we do is, yeah, we have this variable that we compute here, no shadow. I think I have soft shadows here, which actually looks at the neighborhood pixels. It's also ask, it looks into a neighborhood of pixels and asks whether they're also in shadow or not. Okay, so this one, this for loop here, which is, I think, a 10 by 10 window, I'm not sure. So it's basically asking neighborhood fragments and asking the same question for them, whether they're in shadow or not. And it's this no shadow is then computed as a percentage to create soft shadows with not sharp boundaries, but blurry boundaries. So you can just if you want to have hard shadows, you can just have it like this. You can just have x is equal to 0, y is equal to 0 here. Yeah. So this one you can have as 0, 0. You don't add anything to that. So let me quickly do that. Let me take this part into comment and to show you hard shadow, I mean the default implementation quickly. It's just an if statement. With a single if statement, what we are going to be doing is we are checking our light vertex position. We use it, so this is what we get from the, we use its XY coordinate to query the depth map, and then whatever we get from the depth map, this is the depth we get from the depth map. We compare it with the depth of the fragment, and this is our epsilon. If it will, this node shadow will either be 0 or 1. So if it's 0, no shadow, then it means that in scene shadow we multiply diffuse and specular with 0, and it's rendered with only ambient. Okay, if it's in shadow, if node shadow is equal to 1, it means that it's not in shadow. This is where we have 1.0. Diffuse and specular is added. So let me quickly, I just updated the fragment shader. When I run it again, oh, there's maybe everything is in shadow. Maybe I made a mistake there. So it's everything is in ambient now. We don't get into, do we have, so let's see what I have here. No shadow plus equals. Oh, I'm dividing by 25. That's the reason. So when you divide 1 by 25, it's like almost 0. Okay, that's why we get a darkened image. So this one, dividing by 25, was used to, since every pixel for soft shadow contributes 1.0 to this shadow, I was renormalizing it to a value between 0 and 1. So that was my mistake. So when you do it like this, so this is the shadows are now hard shadows. I don't know whether you can see, and now the shadow boundaries are really sharp. They're just black and white, like type of thing. And if you want to have soft shadows, you just, now this time we comment this part out and uncomment this part, and this gives us soft shadows. Okay, yeah, let's see. Yeah, look at the boundaries of the shadows. They are like blurry. Okay, so I'm going to share this code with you on Oticlus. But let's quickly, I have a couple of slides left with some examples, actually, nothing more. So there are some links to shadow mapping for some tutorials. There's an OpenGL shader GLSL implementation, which I'm going to share my implementation with you. There's also the shadow depth buffer that you use when you're rendering from the light's perspective. Since it's an image space algorithm, your shadows are going to look zigzag like this if your resolution of the depth buffer is not large enough. So when you look into my code, you're going to see that although the image is an 800 by 800 image, when I'm rendering the frame buffer object from the depth buffer from the light's perspective, I increase the resolution by 16 by multiplying both parts by 4. So it becomes a 3200 by 3200 image. I multiplied that 800 to have a more high detailed resolution depth buffer. Okay, so the resolution of your depth buffer changes, affects the way these look. Also, we may have artifacts if certain parts are outside the region, viewing region of your light source. Those parts may seem to be in shadow. And yeah, we can have soft shadows, hard shadows. I talked about that. And here are finally some examples that use shadow maps. Many games use shadow mapping algorithm. Here are some example games. Assassin's Creed. And that's my final slide. So with the additional 10 minutes of time, we were able to finish the entire shadow of algorithms. If you have any questions, I'll be happy to answer them. I will stop recording at this point, and this concludes our course this semester. Thank you all for attending. I hope you like the course.